Thanks, Yury. Tonight's speaker is Dr. Lingli Zhou, who is a research fellow in critical mineral resources. Her research interests include critical mineral resources, geochemistry, applied and analytical mineralogy, and sedimentology. Her past 15 years research covers a broad geochemical and mineralogical transformation processes from deep down to the mantle up to the Earth's surface. Dr. Zhou completed 2 PhDs from Chinese Academy of Sciences in 2014, as well as at Ubers University in 2015, respectively, and continued her geoscience career as a postdoctoral research fellow / research fellow in universities of Ireland. She's currently with ICRAG at UCD. So Dr. Zhou, over to you. Please take us away.
Thank you very much, Halleluya, for the introduction, and also thanks to the organizers of the Ore Deposits Hub for organizing the event. Oops, it doesn't work now. Here, let's go. So I welcome everyone to my talk today. So for the following 1 hour, we will going to Ireland. We'll be traveling to Ireland, which is shown from the background image here. And for the presentation, we're going to show you some of the work from a project which we have been working on during the past 2 years, which investigates the critical metals in the Irish zinc lead ores and tailings from a geochemical and mineralogical perspective. The talk will be divided into 3 parts. First, I will give a brief introduction of the critical metals. Then we'll come to the critical metals in the Irish zinc lead ores, mainly sphalerite. And lastly, I will share some preliminary results from a case study of critical metals in the Irish tailings. Before we go to Ireland, let's stop by UK and have a look of the United Nations Climate Change Conference 2021, which is the COP26. There are several goals to reach for COP26, and the first one is to secure global net zero by middle century and keep 1.5 degrees within reach. And to reach this goal, countries will need to accelerate the phase out of coal, curtail deforestation, speed up the switch to electric vehicles, and encourage investments in renewables. So how do critical metals and minerals fit into this? So first, it is fundamental to recognize that electrical vehicles and renewable technologies are made from metals and minerals. The demand for those raw materials will continue to grow. Secondly, it is extremely important to ensure sustainable supply of metals, those metals and minerals, in particularly those ones being defined as being critical, alongside the protection and restoration of ecosystems and in support of local communities. So this has put the mining industries almost at the sharp end of a global debate. So if you simply input COP26 and critical metals in Google search, there will be hundreds of news popping out, and I just list 3 examples from here. And the important roles of critical metals in developing renewable technology and electrical vehicles is highly visualized from this image, which is from a report of European Commission in 2020 that assess the raw materials that are critical for strategic technologies and sectors in the EU. As we can see, it includes a relatively long list of metals. And within these metals, we can still divide them into different levels according to their criticality that are mainly defined from 2 main factors. That's the economic importance and supply risk. So not only EU, but there is a global concern about the availability of critical metals and minerals. For example, earlier this year, Canada announced its own list of critical metals and minerals at the PDAC, which is rather similar to the list of the United States. Well, for China, there hasn't been an official list of critical metals and minerals, but recently there have been several major funding schemes around this topic. So we expect to see an official list coming out in a very near future. In general, the list of critical metals and minerals vary slightly from country to country, but they share something in common. Many of the metals listed here, they are actually minor metals that typically occur in relatively low concentrations of less than 0.1%, in which case they rarely form viable deposits of their own and instead occur interstitially in the ores of a major metal and being produced as byproducts during processing the major metals. For instance, germanium and indium can be produced during processing the chief zinc ores, that is the sphalerite. From a mineralogical point of view, it is reasonably well understood. Sphalerite has quite a simple crystal structure and chemical formula, which allows the incorporation of a range of trace metals, including germanium and indiums. So, speaking of zinc resources, we have to highlight the important role of Ireland in the global context. Ireland is one of the largest zinc producers in Europe. The currently active mine Navan, which also named Tara in Ireland, is Europe's largest zinc mine and also one of the largest in a global comparison. Impressively, Ireland is ranked first in the world for zinc discovered per square kilometers. With 50 years, exploration has resulted in the discovery of 5 major deposits and 20 prospects. More importantly, the Irish carbonate-hosted zinc-lead deposits display many unique features, representing a hybrid of ZX and MVT types. So this has somehow shaped the outline of this project. We want to define the concentrations and the distributions of the critical metals in Irish zinc-lead deposits, including both the sulfide zinc sulfide ores, sphalerite, as well as the tailings. So first, let's have a look of the geology. Most of these zinc-lead deposits in Ireland is hosted within the lower Carboniferous carbonate rocks and concentrated in the central part of Ireland, that is named Irish Midlands. And beneath these carbonate rocks lies the Devonian red sandstones, which in turn unconformably lies above these lower Paleozoic basement rocks, which is a volcano-sedimentary successions that were deformed and underwent weak metamorphisms. And if you want to know more about the geologies, I recommend my mentor's paper, published in 1996, so give a really good comprehensive summarized overview of the geology of the Irish deposits. So if we take a cross section along the Irish Midlands, we can see that most of the mineralization in the south part is hosted within the Wasatch limestones. While moving to the north, the mineralization Navan group becomes the primary host rock of the mineralization. And both rock units are the stratigraphically lowest and long argillaceous carbonate units, reflecting the control of rock permeability on the mineralization. The ore bodies occur in a straight bond, and many display in a stratiform morphologies. And the thin sedimentary normal force is very important in controlling the flow of the ore-forming fluids. Sphalerite and garnella are the major sulfide ores. Barite and iron sulfide commonly exist in variable contents. Minor copper sulfides and sulfur salts also occur locally. And the mineralization occur mostly in massive sulfides appearing replacement texture, and also commonly in veins and open space fillings. One important feature that separates the Irish zinc clade deposits from the MVT and CITIX deposits is the timing of mineralization. The mineralization in the island in Irish type deposits occur mostly during diagenesis with minor syngenetic components. So there has been a wealth literature, and research carried out to define the genetic mode of the Irish zinc-clade deposits. Essentially, the mineralization is resulted from the mixing of two distinct fluids. One fluid is rich in metals and low in sulfur, and quite hot and moderate in salinity, which you might be imagined similar to the Guinness. And these hot, dense fluids that circulated down to the basement, leach the metals, and along with the basin extension and maybe with some driving from the emplacement of the mafic intrusions, it migrates along the normal faults, and mixing with another fluids that is high in sulfur, high content, rich in sulfur, but low in temperature, high in salinity. And the mixing has resulted in the precipitation of the sulfides in the permeable rock units. So here are some photos showing the mineralizations. The first one is a high-grade massive ore from the Navan deposit. As we can see, the sphalerite appearing in massive textures with some granilla and marcasite, pyrite, together with some later stage barite and calcite that are replacing the host rock and micrite. And this is an image showing the open space filling textures. As we can see, some of the sphalerite with pyrite and marcasite, the filling the porosities that between the classes of the micrite. So from the hand specimen, and the sphalerite mostly appear in a fine grain texture, and also in a pale to whitish brown color. And this is how they look like under the microscope. And the textures of the sphalerite is highly variable. It can appear in some of the coliform textures, and also could be in a massive and anhedral textures, and could also be appear as a clasts. And granina is intergrowing with the sphalerite, as it occurs either in a small anhedral morphologies that could form overgrowth along these sphalerite. It can also appear in relatively large subhedral to euhedral crystals. Iron sulfides also commonly exist in some of those deposits, for example, Lixing. And here is an example showing the integral of the marcasite and pyrite. Locally, they would also see some minor occurrence of those well-laminated sulfide layers, and you could locally contain some sulfide clasts. And for this project, we have collected samples from 9 deposits and have more than 100 sections made. And based on these sections, we carried out extensive microscopy work and in-situ geochemical analysis, including both the SEM and laser ablation ICP MS. And with the laser, we applied first the spot analysis to precisely determine the concentrations of those trace metals in the sphalerite. In order to understand the element correlations along the grain scale, we applied the rasters and laser mapping. So in total, we have analysis around 1,500 sphalerite spots, to give a quite relatively good understanding of what the critical metal contents in the Irish sphalerite. So this is what the results have shown. In terms of germanium, it show there's the main is about 66 ppm out of this 1,400 spot analysis, and gallium is relatively low. It's around the main value. The main is about 9 ppm, and indium is extremely depleted. Most of the analyses are below detection limits, or those show values give a mean of about 3.6 ppm. So we can say that the Irish sphalerite show a moderate enrichment of germanium and quite depleted in gallium or extremely depleted in indium. So you might be wondering that what those numbers means in terms of the economic viabilities, especially for germanium. So let's actually first have a look at the price of the germanium. So it looks pretty good for both the germanium metal and germanium dioxide. The price is around $1,000 per kilograms. So just for comparison, for zinc, it is about $2.8 per kilograms. So it looks quite promising. What about the economic potentials of the germanium in Irish sphalerite then? And the board production of germanium is actually not very small, and mainly coming from as byproducts of zinc ore produced from byproducts of zinc ores and copper ores, and could also be produced as byproduct of coal. So we can do a rough assessment of the economic viability of the germanium by comparing the germanium contents in the Irish sphalerite, and in this case, the active mines in Ireland, that is the Navan, to those that are in production of germanium. So this is the list of these values of the numbers, and we can actually see that most of those, the germanium in the sphalerite that from those mines in production of germanium is around 100 ppm for zinc grade of, let's say, roughly around 10%. Well, in comparison for Navan or Tara, it shows some kind of potential, but let's say we may need another push of the germanium price. So that is the economic aspect. We still would like to understand the incorporation mechanisms of germanium in the Irish sphalerite, and so we applied a laser ablation along the sphalerite, along the sphalerite. And in this case, it's a coliform sphalerite from the Galmois. And we can see that along these ablation lines, has transected the core of this coliform sphalerite as well as these coliform bands. And we can actually see that the iron contents along these ablation lines of this sphalerite, it's relatively stable. Well, for the trace elements, it is a different case. So the trace elements show a relatively dramatic decrease when it comes to those coliform bands, and that is the case for germanium, as well as for arsenic and silver. And we also notice that the variation of the germanium contents is correlated closely with the variation of arsenic and silver in the sphalerite. So it does seem that the incorporation of germanium in this sphalerite is closely related to the concentration or availability of arsenic and silver in the fluids. So and this is this is kind of being confirmed by some geological observations that from the silver mines, where locally there's some enrichment of germanium that could appear in germanium sulfide minerals, which is the iagorite. And this iagorite could appear, and together with some other exotic minerals, such as those silver arsenic sulfides, and as well these argillite could also appear in a massive ores. So it does seem that where the enrichment of germanium occurs, the fluids also relatively enriched in silver and copper. So that is some kind of the first conclusions from this work. The moderate enrichment of germanium in the Irish sphalerite was probably favored by the availability of trace metals, including arsenic and silver, in the hydrothermal fluids. So moving from the sphalerite ores to the tailings, we still would like to know what has these critical metals have become in the tailings after sitting buried in the tailings for long. And we took a case study of the Tynagh deposit. The Tynagh deposit was into production in the early 60s and was closed in 1980s. So the tailings has been sitting there for almost 15 years. And the mineralization occurred in the Wasatch limestones and closely associated with the activities of the Tynagh fault. And the ore bodies consist of a primary sulfide ore bodies and a secondary ore bodies at surface. The primary ore bodies are comprised of massive zinc and lead sulfides with barytes, and the secondary ore bodies at surface comprised of sand, gravel, and boulders in a fine mud matrix. And the minerals in the primary ore bodies consist mostly of sulfides and barite and some of the sulfur salts. Well, the secondary ore bodies contains both sulfides and also some products, the weathering products of the sulfides, including the carbonates, silicates, and hydroxides and oxides. And this is how the Tynagh mines look like nowadays. And our samples come from the tailing ponds, which are located here. In total, we have about 23. We have 23 samples connected, and those coarse reject samples were prepared into a 1-inch resin block, and we did quite extensive microscopy work on these resin blocks to characterize the mineralogy, as well as some of the interesting textures that reflecting the secondary process. And then based on those microscopy images, we select areas of interests and did some ACM work. And this includes these to identify those zinc mineral rich phases, and as well to show some the interesting textures in a higher resolution. And further to that, we also select some of these large grains of the zinc mineral phases we identified and carried out the laser ablation ICP-MS work to measure the trace element contents in those zinc mineral phases. So let's have a look at what we have found in the Tynagh tailings. So firstly, it's quite interesting. Actually, we find a rhomboidal shaped mineral that is really extremely enriched in zinc. And we name it as a biogenic zinc mineral for now. And also there are some zinc sulfides still left being there. That is commonly sphalerite. And commonly this sphalerite, the zinc in this sphalerite could be replaced by other metals, or the sphalerite would be enclosed by other sulfide phases, and as well as zinc silicate phases, that is a hemimorphite. These hemimorphites looks like they were actually sourced from the secondary ore bodies, rather than forming in situ in the mine tailings, And those mineral phases contains extremely high of zinc, that is in generally above 50 weight %. As well, we identified the zinc hydrocarbonate minerals that including both the hydroxide site and the smithsonite. And those minerals also contain relatively high of zinc that in general range from 40 to 50 weight%. And they also looks like they were probably sourced from the secondary ore bodies. As well, we identified the zinc iron hydroxide, and the zinc and iron content varies in a relatively large range. And as well, we also identified some a mixture, some mineral or some amorphous phase that that is composed of a mix of carbonate and silicates. It also shows relatively high contents of zinc that above 10 weight%. And we also find some carbonate minerals of iron and lead phases that also contain some minor portions of zinc that is in generally below 5 weight%. And those minerals show quite interesting textures that is probably that is very likely suggested they were formed during the burial in the tailings and involving a lot of bacterial activities, microbial activities. And so bring all the information together. So for the Tynagh tailings, we actually have identified a few zinc mineral phases. Some of the minerals, some of the phases are quite high in containing zinc. And one particular one is a biogenic zinc minerals, and then the zinc sulfides and the zinc silicate that is a hemimorphite, as well as the zinc hydrocarbonate and zinc iron hydroxides. But as well, we also identify some other zinc containing mineral phases, including the silicate with zinc and zinc iron hydroxides and some carbonates of iron and lead. And though the zinc contents in those mineral phases are in generally below 10 weight%. Interestingly, if we bring together the iron and metal lead contents together in comparison to the zinc contents in those mineral phases, we can actually see that those zinc-rich mineral phases in general depleted in iron and lead, while these zinc-depleted, relative depleted mineral phases, they are enriched in iron and lead. And this reverse correlation is even more obvious from these binary diagrams of the zinc and lead, zinc and iron contents. We can actually see there is a clear reverse correlations. So this brings to our second conclusion of this project. There seems the abundance of the iron could probably affect the formation of the secondary zinc dominant mineral phases that transforming from the zinc sulfide ores. So what about those critical metal contents in those zinc mineral phases we have identified? So this is what the laser data have revealed. Let's look at individual for those critical metals. So for galliums, we can actually see that most of the zinc mineral phases contains galliums, and have a concentration and the mean concentration around 10 ppm, except that the zinc silicate phases show relatively high gallium contents. While for germanium, it's slightly different. Some of the zinc mineral phases, like hydroxides, they're in generally absent in the germanium. While those containing germanium, those mineral phases containing germanium have a germanium contents around 10 ppm, relatively consistent. While for indium, it's in general depleted in all the zinc-rich phases. So, and also if we bring together, if we make a comparison of those metals in the sphalerite ores to those secondary mineral phases we identified, just to gain some insights of the, to have insight of the gain and loss of elements during the transformation process, we can actually see that in comparison to the gallium contents in the sphalerite, most of the secondary zinc mineral phases show enrichment of galliums. Well, if for germanium is relatively stable, there is not much gain or loss. Well, for indium is in generally depleted, not much could be seen there. So that actually shows that there is an enrichment of gallium occurred during the formation of the secondary zinc minerals, while these germaniums is rather stable, sitting in the tailings or during the secondary process. So so we also want to actually to understand how this enrichment or gain of gallium have occurred. We might have some insight from these bulk analysis of these tailings that we sent to the LS labs. And by applying the principal component analysis to the geochemical composition of these tailings, we can actually see that the gallium is closely associated with the silicate mineral phases in the tailings. And that could possibly mean that during the alteration or decomposition of these silicate mineral phases, gallium probably could be released and being incorporated in those secondary zinc mineral phases. So that brings to our conclusions. We have some of the preliminary results coming out from this project. The Irish sphalerite contains appreciable amounts of germanium, and they're low in gallium and extremely depleted in indium. And the enrichment of germanium was probably favored by the availability of trace metals, including arsenic and silver in hydrothermal fluids. And for the tailing part, we can see that the formation of the zinc-rich secondary mineral phases is affected by the abundance of iron in the environment. And in terms of the critical metals, the germanium is selectively deported in the secondary zinc mineral phases in the Tynagh tailings. And the decomposition of the alteration of silicate mineral phases in the tailings could probably have contributed to the gain of gallium in the secondary zinc mineral phases, in particular for the silicate phases, hemimorphites. So we still have some ongoing work of the tailings, and we're looking at those tailings from the Gamoy at the moment. And we also have actually a lot to understand. We do have a lot of data, but there's still a lot of to understand why it was appears like that. So lastly, I would like to acknowledge the founding agent of the Geological Survey for the project, and also many individuals and companies for supporting this project. And also thank you very much for listening. I'm happy to take questions.
Dr. Zhou, for that interesting talk, for taking us through these different critical metals within the Irish ores and tailings. And I see we have so many questions, and I think I also have some from the exploration point of view, but before we get to the question sections, I'd like to call upon Dr. Max Frenza. He's also an equally advocate of this topic on critical metals. So Dr. Frenz, the floor is yours. Give us your inputs, your ideas, or any questions that you might have for the presenter.
Hello, Lingli.
Hi, Max.
How are you? That was a very interesting and great talk, and I have actually got a lot of questions. I'm not sure we're going to get through all of them, but let's maybe start with the sphalerite study. So those 1,500 spot analyses, how many samples are actually behind that? So how many individual tin section samples?
Well, for Lixin and Tara, we have relatively good amounts of thin sections. Mm-hmm. That is roughly around, for Tara, we have about 10 thin sections, and for Lixin, we have about 20 thin sections. Mm-hmm. And for other deposits, in generally, we selected about 6 thin sections, around that number.
Okay, so overall, you have something like 50 samples, 50 to 100 samples, something like that. I can't remember how many deposits it was.
9 deposits. 9 deposits. Yeah.
Yeah. Okay.
It's around 50 to 60 in sections.
Okay. So my main question then is like, did you look at the differences between the samples and the differences between the deposits? Right. I would expect them to be quite large. And is it like that 67 ppms that you calculated as an average of the spot analyses, can that be considered representative for the Irish mineralization if you do that?
Well, in general, so we can actually also look at the range of those germanium contents. It's most of these spot analyses are within the range of 0 to 200 ppm, and and they're not evenly distributed. I would say some of the mines, such as Abbey Town, it contains relatively high contents of germanium, to let's say 200. The mean values of Abbey Town individually is about 200 ppm roughly. Whilst for some of the other deposits or prospects, they are quite relatively low in germanium. So this mean value of 66 ppm is almost like taking all the consideration of all the data points, but individually there is a difference. And that is great, actually, because it helps us to understand what might be actually the reasons for some of the enrichment of germanium, let's say occurring in Abbey Town or in silver mines. Silver mines also has hundreds of ppm germanium. So some Tynagh actually, if you notice the sphalerite contents, which I put in the last in comparison to the tailing analysis, it's actually relatively low. It's below 10 ppm, the mean values. So from the sphalerite ore, at the beginning I was thinking maybe it was because the sampling was biased, and because we don't have a large collection of samples. But then actually in comparison to those sphalerites in the tailings we analyzed, it also is around that tens of ppm, in general below 50 ppm. So we probably think it is actually represent a relatively low concentration of germanium in the Tynagh sphalerite. So yeah, individually there is a difference, and that is the difference is great. And I'm trying to find clues to understand what is the mechanisms controlling these differences. Might be the source, might be the fluids.
Temperatures.
I'm not sure temperature might be the reason, because some of the deposits that are relatively similar in fluid, similar in the temperature of the ore forming fluids, let's say silver mines and Lishing, there has been fluid inclusion work being done and suggests the fluid temperature are rather similar, but in terms of the germanium contents in the sphalerite, there is quite large differences. So I'm thinking now the temperature, for sure, 10 pH probably is not a factor either, because they are in generally buffered by the carbonates. There's not large variation in terms of temperature, pH. Then might be actually maybe the sulfur fugacity in the ore forming fluids. So that's my thinking. Also, if you think about where the silver mines, which I should, which is actually we're calling, I see Colin left some comments there. He saying he gave me, show me some photos of where those germanium minerals occur, and they are closely associated with some of the arsenic, arsenic sulfides. And it means actually the fluids are probably super enriched in, it reflects the sulfur fugacity in the fluids. So arsenic probably can commonly replace sulfur in the sulfides, but in this case, it forms a sulfur related mineral. I can show you where the slide is. So you can see the mineral associations in these massive, let's say, ores, and all these exotic minerals issues enrichment of germanium, silver, as well as arsenic. And commonly arsenic could probably choose to replace sulfur in the sulfides. But in this case, I imagine the sulfur fugacity was probably quite high in the ore forming fluids. And the arsenic is also probably very saturated in the ore forming fluids. And it started to form some silver arsenic sulfides. So that is my guess of the enrichment mechanisms of the incorporation mechanisms of the germaniums.
Well, argyrodite is a mineral that normally occurs in epithermal systems, if ever, anywhere. It's very rare.
Yeah,
I'm not sure, like as long as you haven't actually seen it, that this correlation that you see between silver, arsenic, and germanium might not just simply be that they go together in the fluid. Also because we don't understand so well how sulfur fugacity does control the germanium contents.
Yeah,
because there's no data.
Yeah, we know so little about germanium.
Yeah, but what I was sort of really getting at is that if you have such large differences between your individual deposits, then maybe if you're going to like say something about economics, it makes sense to say it by deposit. And obviously the most interesting one here is Navan because that's still operating. The other ones are not, like things that are not producing zinc concentrate maybe are not terribly interesting these days, because if ever you would extract the germanium at the smelter from the zinc concentrate.
Yes, indeed, I agree. I think for the comparison of the germanium contents to those mines that are in production of germanium, I put the Navan mines and the values of germanium content are actually used. It's the mean value of the for the sphalerite from Navan rather than for the entire data sets. So I totally agree in terms of economic viabilities, we have to do it individually.
Am I allowed to ask some questions about the tailings too, or would you like me to stop at this point? This is towards the moderators.
I'll give you another chance to ask, so go ahead, ask your question, Dr. Frenzel.
All right, okay. So for the tailings, my first question again would be one of like representativity, more or less. How did you take your samples?
It's a great question. Actually, I think John and Julian is here. So John and Julian, they works for the they works in the Varangian Metals Island, which is currently looking at reprocessing the Tynagh tailings. So when we were in touch with them, we were also considering whether our sampling would be biased, because it's relatively large data. It's a tailing ponds, and if you just get several drill cores, I have 23 samples. We couldn't say much of the entire economic potential of those reprocessing the tailings. So we talked to John. We asked. We fully believe in the in the local geologist, I would say. We asked him so if we want to select samples, what would you recommend first place of which drill cores we select? And John gives us some very good advice, and based on his advice, we picked some of those drill cores of the tailings. And for the selection, there are some considerations because we know that some parts are relatively rich, or I think John was original. No, some parts are relatively rich in zinc lead. So we preferably pick samples from those places, because if we considering reprocessing tailings, those actually have the priorities of being considered. And if we can know that many critical metal contents there, they might also be preferably considered as well. So that's our choosing consideration of sampling.
So you took composite samples of entire cores, or you took grab samples from like bits of the core?
So we have picked, let's say here, we have four, we have samples from 4 drill cores, and then at each different, distributed at different depths of the drill cores. The idea was also look at how the geochemical varies at different depths of the drilling of the pond, of the tailing ponds as well. I have the data, we just didn't show it here, but we'll make the story a bit more complex.
Nice. Okay. Right. That's good.
Yeah, our first thought is probably really we want to actually determine the critical metal contents in different zinc mineral phases. So I think in this case, maybe it's not very much, it doesn't really matter so much of whether our sampling is biased or not, because it still matters, but probably it's not the most important things to consider. Do you understand what I mean? Yeah.
Provided that, you know, you at least have all the minerals that you would expect across the plant. Yeah, okay. But what are the actual contents of metals in these things? Is it actually worth looking at them? That's so how much zinc, how much lead have?
There's pretty high zinc and lead in some parts of the tailing. That's what I could say. I'm not sure Julian would comment on that, but definitely viridian metals are considering reprocessing some parts of it using some economic ways of reprocessing, of course. But also one good thing of reprocessing the tailings is that they are already quite fine in grain size, so you don't need to crush them and grinding them. You save energies, you save the monies, I say. So
what does pretty high mean? What does pretty high mean?
Economically viable. So
yeah, so we're talking sort of 5% lead plus zinc.
Some parts are more than that, because I would say historically, the mineral processing of the Tynagh, it was not good for some period of time. That's led to some very good metals, or the sphalerite ores actually went to the tailings. So that's also the consideration of the reprocessing the tailing now.
Maybe just to add to that, just to thank Dr. Frizzell for your contribution, maybe to add that this work has not been published yet. So I'm sure we'll be able to see actual numbers when the work is finally done and published. With that said, I would like to thank you for your contribution. And Yury, do you have the next question for Dr. Zhou?
Yeah, so we have plenty of questions posted in the chat. And for a start, I was curious, did you measure the mercury? So there was a question from Azam Sultani regarding mercury, if you measured this at all. And if it is, then what is the relation with other critical metals?
So do you mean the mercury in the sphalerite ores or the tailings?
Yes, in ores.
In the ores, yeah, we measured mercury. The mercury content is not very high, which I mean not very high, definitely it's below hundreds of ppm. And the correlation with the critical metals, it doesn't show much correlations. And but we find something interesting is that some of the critical metals actually show germanium show negative correlation with cadmium contents in general for the Irish sphalerites. And we also try to understand that because cadmium, we also know very little about it. So that's it.
Thank you for that answer. I would like to give a chance to Filipa. Filipa has tons of questions for you here. So Filipa, over to you.
Okay, thank you so much. I will start just with two quick questions, more specific about the geology of deposits. So the first question is, do you think mafic intrusions have an important role on kind of critical metals they can carry and be leached for the ores? And do you believe if you have felsic intrusions, do you expect to have the same kind of metals on sphalerite?
So in terms of first questions of the contributions of the mafic intrusions, so the contribution of the mafic intrusions for now is just referred to be to contribute some the emplacement of those mafic intrusions provide some of the drive to drive the fluids moving upwards, because it's a relatively large volumes of ore forming fluids to forming the Irish zinc late deposits on regional scale. So just the extensions along with the basin, with these basin extensions are probably not sufficient or enough to drive those ore forming fluids. And that makes people think, some researchers think that the mafic intrusions could have actually contributed to the mineralization by providing the driving force. But in terms of if it contributes to the metals, actually there is a Limerick basin in Ireland where there are some igneous, there are a lot of igneous activities going on there, where you can really see the igneous intrusions. Well, in those deposits I was talking about, it doesn't really show any genetic correlations with the mafic intrusions. Another important thing actually to define what is this Irish type, or in general these carbonated host sedimentary related carbonated host zinc late deposits. It's genetic. It's genetically not related to igneous or magmatic events. So in this case, I would say the mafic intrusions provide materials for the mineralization, but more likely providing a driving force to move the fluids upwards. So do you mind repeating your second question, Filipa?
Oh, that's fine. You answer with that. It's okay. I understand that in this case, probably does not have any importance. My second question is quite quick. Besides sphalerite, there are any other minerals on Irish ore that can incorporate these critical metals?
There are also some copper sulfides. We analyzed a few samples. It also shows some kind of inclusions of critical metals in terms of indium mostly, not really germanium. But I have to mention here, I probably didn't have time to go through that during the presentation. What I mean Irish type deposits here is actually related to those. It's in Ireland, there are also some MVT type deposits that occurring in the Kildare district. They show very distinct mineralizations in terms of the morphology and also the mineral associations, quite different from those ones I was just talking about, or where our samples coming from. So and as well, there are also some VMS deposits in Ireland. So so what I'm talking strictly of what the data about is mostly from these classical Irish type zinc-late deposits.
Okay, thank you so much, Lingli. I have a lot of questions, but I will give you the word to another person. I would like to call Gideon Lambivi. Do you want to unmute yourself and ask the question? I think.
Yeah. So thank you very much for the opportunity. I was just wondering, because you mentioned that beside the primary mineralization, you have secondary mineralization before and overprinting weathering processes. But in the principal component analysis diagram that you have shown, it seems like gallium is associated mostly with the silicate phases. And I remember you mentioned that some of the zinc silicate mineralization minerals that you showed are likely results from secondary mineralization and not a product of weathering. So why, when you look at the principal component before you make a conclusion on the principal component analysis, why don't you think that the minerals that you are seeing, the gallium that is associated with those secondary, with those silicate, is coming from secondary mineralization and not inherited from the breakdown of primary sphalerite? I don't know if my question is clear.
So these sphalerite in generally quite depleted in galliums. Let's say that in general below 10 ppm, while for the silicate mineral zinc mineral phases, it shows around between 60 to 80 ppm galliums contents. So it would be relatively difficult, let's say, in terms of mass balance, just to have that amount of enrichment of gallium to occur in these silicates in the hemimorphized phases. And from the principal component analysis, we can actually see that those aluminium and potassium is the gallium, or the trace metals are closely in relation to those potassium and aluminium major mineral phases. And we also indeed from the mineralogy optical from the microscopy work, we also see quite a lot of silicate mineral phases, particularly the feldspar. So that's, and from the bulk analysis, some of the samples also quite high in those aluminium and potassium contents. So that make our guess that this gallium actually associated with some silicate minerals that could be, let's say, feldspar or other silicate minerals.
Thanks, Lingli, for that answer. Before we wrap up, just a couple of questions that I would like to ask, if that's all right with the presenter. Can we ask you a couple of more questions, Dr. Zhou?
Yeah, sure, of course.
There is a question from Colin. I would like to ask Colin Injo to please unmute. If Colin is still around.
Yeah,
please.
Still here.
Yeah, all right. Thank you. Go ahead.
I think you actually mentioned it, Lingli, about Kildare. The Kildare deposits are clearly not Irish type. And I was just wondering, have you got any germanium analysis on the sphalerite there, was the first question.
Unfortunately, we haven't. It would be really interesting to actually have some data from there. because MVT type of deposits, the fluids are generally low in temperature in comparison to the Irish type. So it would be really interesting to see the control of all forming fluids on the germanium contents.
And the sort of the second point I was interested in was that there's been a few other people who mentioned mercury. The only mercury of significance in Ireland is a goat drum. And I was wondering if you looked at any germanium, gallium, or any other exotics in the goat drum mineralization, because there's quite a large tailings pond there as well.
We haven't either. I think there's still quite a lot of work to do. But what I could say is that we actually, what I just mentioned, the germanium, the correlation of germanium with the cadmium. And cadmium, Colin, you probably know that, the Keel deposit, it is relatively high in cadmium. So we did some find that most of the sphalerite sports from Q are quite low and really quite low, below 10 ppm of germanium, contains relatively low germanium, below 10 ppm. So it seems a really good correlation of, let's say, what is the relationship between germanium and cadmium. But we also see that actually interesting Q, we also see some sports that show extremely high contents of germanium, but low in cadmium. So it does seem Q, there may be at least 2 episodes of fluids or mineralization occurred there that are distinct in the trace elements from the sphalerite geochemistry. But yeah, that's my answer.
Okay, thank you, Lingli.
Yury, do you have one more question for the presenter before we let her go?
Okay, so I guess the last question, if Taring Kerwood is still around, would you like to ask the question yourself?
Sure thing. Lingli, thank you very much for an interesting talk. I was just wondering, if you've got multiple samples from each deposit, is there much of a variation, sort of any zonation in your critical metal content across the deposits? Say, sort of proximal to the feeder fault versus distal or anything like that?
Thanks, Tari, for the question. It's actually a very interesting one, and we've also been thinking about it. Or probably that's part of the plan for the original projects. So we have multiple samples from one deposit, and some of the deposits will have quite well constrained geology informations, but it's probably not coming to the point that we can actually use it as a vector tool, thinking about the sampling. But we do now, what we are working on is actually try to identify the different generations of sphalerite and to see those, the critical metal contents associated with how it varies or changes from among these different generations of sphalerite. So it's more a temporal relationship rather than a spatial relationship.
Cool, thanks. Look forward to reading about that.
All right, we are at the end of the talk, and unfortunately, apologies to anyone that has put a question in the chat box and I haven't gotten to it. But I just would like to thank the speaker for the amazing talk, and would like to also thank Dr. Max Frensel for his contribution and everyone else that has contributed in forms of questions or comments. And just a reminder, Dr. Lingli Zhou's work is not published yet, and we will be sure to share the content with exact numbers and all the information once that work is available for public view. With that said, I'd like to thank everyone for attending, and see you in 2 weeks' time.